YouTube transmission.
Okay.
Huh? Anyhow, and just know anyhow, guidance. I'm just going to introduce you now. Okay. Okay, so what are the present? Some people do call their talking. I'm sorry, it's the YouTube view. Então, pessoal, boa tarde. Obrigado pela presença aí de todos vocês. É um grande prazer, né? A gente está começando as atividades desse evento do Bingo que a gente organizou aqui com tanto trabalho, mas assim, tanta empolgação para receber todos vocês. Então, nesta semana nós vamos ter aqui o Bingo Collaboration Meeting, a versão 2023 desse evento, né? Então, esse vai ser um evento geral da colaboração, onde a gente vai passar várias informações, estados atuais da colaboração, divulgar o projeto, vai ter atividades envolvendo estudantes de ensino fundamental, ensino médio. Então, a ideia é ter um evento bastante amplo. E aí, como um pontapé inicial, a gente está recebendo aqui a visita do professor Jiajun Zhang, do Observatório de Xangai. O professor Jiajun é um dos nossos colaboradores, né, dentro da colaboração BIM, né? E é a primeira vez que ele está visitando o Brasil, a primeira vez que ele vem para Campina Grande. É um grande prazer ter você aqui, Jiajun. So, I'm saying that we are honored to have your presence here. It's very, very nice to meet you in person. And we're pleased to have you in Brazil, in UFCG. And then today, Jiajun is going to talk for us about the Chinese new telescopes. So it's going to be a very interesting presentation with general topics. So it's not a technical presentation about telescopes or about BIGO. So thank you so much, Jiajun. It's a pleasure to have you here. So it's all yours. Okay.
Thanks for John's invitation and also thanks for his introduction. So my topic today is quite general topic itself. It won't be very technical as already introduced here. And in case you have any questions and you don't understand something, you can just raise your hand and ask questions to totally fine. Myself, my name is Jiajun Zhang from Shanghai Astronomical Observatory. Shanghai Astronomical Observatory, as you know, is located in Shanghai. But Shanghai itself is not a very good position for observation because bigger cities, they usually generate too much noise for telescopes. So it's usually not a good position for telescopes. But we still have some of those in the site. For example, this one. Yeah. Okay. So in backend here, so this telescope, you can see itself has a diameter of 65-meter diameter. And itself is fully steerable, means that it can locate and point at any direction in the sky. All right. So there's a rover, actually here, there's a rover, so it can roll the whole telescope in this way. And then it also has a steerable part here, so that it can move the telescope in this way. So put them together, it can point at any direction in the sky. So this one was located in Shanghai. It's located in Shanghai, and the name of this telescope is called Tianma Guangjingzhou. Actually, it's already written here. The Tianma telescope, or in short, Tianma. So this is basically built in 2012. By our observatory. And so let's just go back to some very basic questions and ask. A very basic question. So what is the most basic instrument for us to do observations? Any ideas of what kind of things we use? Very basic things, any word?
The eyes.
Yes, sir. Our naked eyes. Our naked eyes is actually a very good instrument itself to observe. So let's go to an image, sample an image like this. That's an image taken by some telescope. You may guess which telescope take this image. The image itself is beautiful. You have all kinds of galaxies. You have different colors here. Something looks yellow, something looks red. So think about when you use your eye to look at the sky, look at the image like this. What kind of information you would like to get from the image? So the information you would like to get. So currently, these are the information you would usually want to have. For example, when you just compare these two objects inside the white circle, you find one thing is a blue one, another one is a bit yellow or red. So that we need to know that the color of our objects are different. And we also see that there are also some very dimmer objects, but some are brighter objects. So the brightness itself matters. The brightness is small, right? And also the shape. You can see one thing here, the shape is more regular, like a more round object itself, and the other thing is more irregular. And also something else, for example, you can see here this, you can see very clear spirals. So the shapes of the object itself also matters. And also the size, right? Something looks bigger, something looks smaller, right? So these kind of information are usually the information you want to get when you take an image or you want to take any kind of observations. So now here's the answer, which image it comes from. It comes from the Hubble Space Telescope. You know, Hubble, when Hubble tried to take this image, it very actually locates itself, the point itself, at a position where it looks nothing. So it's just pure dark, looks nothing. There's no bright stars, there's no bright galaxies in that direction. And so it just takes a very deep imaging and finally just give you a view of all these kind of objects. They just show you the mysterious part of the universe. So in there, you can see a lot of different kind of objects, and there are all kinds of galaxies over there. How many information you can get from those? It's quite a lot. And so when we define what is a good telescope, we usually want a better telescope, but not good telescope. What good is good? Good telescope means, so think about this information you want to get. You want to get more information, so you want a bigger field of view that also big. Field of view means how wide you can look. With a wider field of view, we can take images at a larger portion of the sky at the same time. And you also want high sensitivity, so that you observe at the location and where you look like nothing there, but if you observe for a long enough time and has a good enough sensitivity, you can see many of these objects. And then further, you want good resolution, so that you can resolve the object and see their shapes. Want to know the shapes, you need to resolve those. And then further, you want a fast viewing, so that you take images very fast. Take one portion of the sky here and then move to another one, and then move to another one, so that you can take the image much faster. If you take fast enough viewing, what things you got? You got a video. Take a video. The video itself is always better than image. So to do an observation like this, I already told you that. For example, in Shanghai, we even have some telescope in Shanghai in the past. It's no longer a good position for observations. So any location inside a big city is not a good choice. For example, if you just take a telescope, put it even here in Copenhagen, I would bet that you cannot see different things. It's not a good choice to put a telescope where too many people and too much light. You want to avoid the people, you want to avoid the population, you want to avoid the light, you want to avoid pollution. So here is a good site that we have found in West China. It's called Lenghu observation site. So this is some remark put over there. You can see in this region, It's totally distributed, no one. Whereas no people is a good position for telescopes. That's the same situation for people. Right? We go to somewhere there is barely any person. Right? So in this location, it have a really bright and clean sky. And in the clean sky, for example, here is the sky that you look at. So you go there and you observe by your naked eyes, you can see the Milky Way on the sky very clearly. So it's a really good position to look. And we put our telescopes, one of the telescopes, a new one. This one is very new. It is so new that it's just built 2 months ago. It's built like 2 months ago. So it's called WFST, Wide Field Survey Telescope. So according to the name, you see that the purpose of this telescope itself is the wide field. So a wide field of view, so that it can take images, take large images of the sky. And then let's compare this telescope to some other telescopes currently in the world. We have many other telescopes in the world. When you compare to, for example, the HSC, DS, or KIDS, or something else, you can see they are somehow at the same level. So more to the upper right means you have a better performance of the telescopes. And so it has many different kinds of scientific goals, like time domain astronomy, solar system objects, Milky Ways, local groups, and cosmology, basically. So this one is a pretty nice one. It's a newly built, very bright. And then if we I already told you that if we take photos for many times at a short time, what kind of things you got? You are taking films, you are taking videos. So you are taking videos. So here is the same. This one is also very new. It's built last year. It's built last year for the Megascope. Megascope itself, the nice thing about Megascope is that it takes 3 colors at the same time. So maybe you will feel weird. So taking colorful images isn't it just very natural thing? So for example, when you take out your cell phone and you take an image, when you take the image, you just got a colorful image, isn't it? But in fact, the instrument itself do not really take colorful images. Usually for the cameras, we use like the CCDs or CMOS. They only take the brightness of things. They do not differ by color. Okay? So how do we usually take colorful images? Especially, for example, in your cell phone, how do you see the colorful images? Actually, they just present the image or filter the light by different filters at 3 different colors or 4 different colors. And they get those brightness of colors in the camera. So that you got those numbers in RGB, red, green, blue, those numbers, and you combine those numbers together, you can get colorful images. So usually for the telescope that we take images itself, we take different colors of image at different times. But if you can think about it, if some object in the sky changes color very fast, you cannot really take it. So here the same we use is this kind of design so that you can take 3 colors at the same time. So it's taken colorful images at the real time to get the colorful video, right? Take a colorful video. So this is the location of this telescope bed. It's in Yunnan, Jiajun at this position, held by Yunnan Observatory. And then, so you know that when you disperse the light, for example, you disperse the sunlight over there, what things you got? You use a prism, and use a prism to disperse the sunlight. You have very colorful rays, right? If you disperse it enough, you get spectrums. You will see some spectrums from these astral objects. From our sun, you will see some different kind of elements. For example, here are the spectrum of several different kind of several different kind of elements. Right? For example, you have the hydrogens. You have these lines for hydrogens. and the other different kind of elements. So basically, every different kind of elements themselves, they produce a different spectrum. So when you observe the spectrum, the pattern of the spectrum tells you what is in object, right? So that's exactly how we know that our sun is mostly composed of hydrogen and helium by observing at their spectrum. We also do the same thing for very remote objects and get to know what kind of elements are coming from. But another good thing about that is another thing we need to mention is about the Doppler. Doppler effect is something that when the things come to you in a certain speed, you really receive the frequency higher than it originally is. And when they move away from you, you get a lower frequency. So here are some experiences in your daily life. You see if a train or a car drive coming to you, you hear the noise of the car higher. And when they go away from you, you hear the noise of lower at the frequency. So for the light, it's the same. But for the light, if they come to you in a very high speed, you have a push. So the color of the thing will become bluer. Or they move away from you in a very high speed, you will find them become redder. So that's exactly how we find that the universe itself is expanding. Right? So looking at these kind of objects, that's the images of objects like a Virgo or simulator, to this hydra. And you take the description of those. You can see here, there are two black lines. And here, two black lines here, They are all representing calcium. Calcium absorption line for these astral gases, basically, extra gases. And so for these kind of ways, in the left, you have the bluer color, and in the right, the redder color. So you find that all these kind of objects, they have some kind of redshift. You see those kind of redshift. And you have the redshift, according to Doppler effect, you think they are moving in a speed, and you record their velocity. You have the velocity in the y-axis and the distance of these objects to you in the x-axis, and you draw them into these data points. And you draw a line, and you'll find the Hubble law. Okay, you find Hubble law, you can plot Nobel Prize. So that's done by Hubble, and when Hubble in 1929, when we try to use this kind of technique to see the expansion of the universe. But that also represents basically the principle of how we want to use window to observe one centimeter line. That's another line of hydrogen. Help us to observe the expansion of the universe more detail. And now when we put these colors in these data points for today's observation, like in 1999, it's already much more than 20 years ago. It will look like this. So you know that spectrum itself is very useful. Spectrum is very useful, tell you the element, tell you the redshift, tell you the expansion of the universe, winning you a Nobel Prize. So it's very nice to have these more and more different kind of spectrums of the objects. Then how to get a lot of objects? Get a lot of spectrums at the same time. Right? That's the problem. So here it is a telescope that we built in 2008. That's called LaMOST. LaMOST is a 4-meter optical telescope. Yeah, looking this way. Quite weird. In Hebei province, and I know you don't know Hebei province. I guess somehow you know Beijing. Beijing, right? It holds Olympic Games in 2008. Where the city can hold Olympic Games is usually a super city. Right? So it's very bright. Not really a good idea to put telescope too close to Beijing. Unfortunately, when we design this telescope, Beijing is not good. So, but the city itself just developed so fast. We cannot afford. So here is in that location here. This is the telescope. How many spectrums can it take at the same time? 4,000 spectrums at the same time. When compared to the other telescopes in the world can take spectrums very efficiently. Something that are very famous for people to know, for example, SDSS, the Strong Digital Sky Survey by US, they take about 800 a time. And our LaMOST take 4,000. So five times more than SDSS, and compare the others. So itself is very powerful. So, and it takes mostly the star spectrums from our own galaxy. So if you say for the astral objects, how many spectrums do you got? Who contributed the most of spectrums that you can get in the world? That's basically this telescope. It contributes like more than 70% of the spectrums. And but we are not satisfied. We're not satisfied by only taking 4,000 at a time. What about just take more? Take more, okay, so let's do not locate too close to Beijing. Let's move to a remote part like the great position we have found in China. There was no people. So go there and put something like this as in design. This is the design of the telescope bus. And here is the current situation. They just clean the ground and looking for putting really things over there. So here we don't really need to know all these words, but you just need to know that it's planned to get more than 10,000 spectrum sets. 10,000. Okay, so then let's move from optical. Let's move from optical. Here, all these are the optical telescopes, or something you can really actually observe by your own eye. That's fine. Then, apart from optical, what we can do from the ground? We build the telescopes usually on the ground because it's cheap. Because it's cheap. So here is the optical window of the atmosphere. So atmosphere itself is not transparent for every different kind of electromagnetic waves. It's only transparent for certain frequencies of waves, right? It's not transparent for all. So it's transparent for optical light here. And you can see this part is not transparent, and for this part it's not transparent. But here is another window, right? This is another window called radio window. Radio signals or the radio frequencies. For these radio frequencies are usually something that we also use daily, like your cell phone, receiving signals, and you use GPS to locate yourself. All these kind of signals are sent by radio signals, transparent. As long as they are transparent, we can use them to do intelligence. Bingo is also radio telescope. So let's just mention one telescope that basically have the same scientific goal as Bingo. That's doing the 21 centimeter mapping. That's Jiajun. Okay. At this corner of China, and this is the figure. So we have this cylinder dish here, and this usual dishes there. So this is an interferometry system of the radio telescope there. And the scientific goal is to do 21 centimeter intensity mapping to see these fluctuations of the universe, and they provide us about the knowledge of cosmology. That's what Bingo would like to do as well. Jiajun was built in 2016, but up to now, there has no successful detection of these objects yet because it's really hard to deal with them. So even though you know the principles, that doesn't mean you can make them into anything. So the next one is this one. I guess you know it somehow from the news. This is by far the largest single spherical radio telescope we can see on Earth. Right? This is this one. Fast is over here. The 500-meter aperture spherical radio telescope. But we also have some idea to say, maybe one fast itself is not good enough. What about building something more? So currently our idea is to build 6 more of this thing in China, so that we can form an array to have a good resolution. So compare. You can see this is fast, and you compare it to a receiver example. And corner here, receiver. Arecibo unfortunately collapsed several 2 or 3 years ago. This is the receiver. Yes, the diameter is 305 meters, and for a part we have a 500 meters. And you can see in the middle, this is the receiver basically we have for the feed, and this is the feed of our receiver. Our feed is also much smaller size because we have a very special design of the So, but you can see fast itself, because it's located in a bed, it used the bed itself to work as a support so that it can form a spherical shape under the bed. But that also means it cannot rotate itself easily, right? You're locked in the bed, you cannot really move at all. So if we want to build a steerable ones, we want the larger steerable ones. Here's another example of a PPT, Jiajun radio telescope. This is the size. Currently, there's nothing, not really nothing. Already some telescopes owned by our Xinjiang observatory. And we plan to build this thing over there. It's 110 meters in the diameter, and it's fully steerable, just like what our PMRT in Shanghai was. But it's just a 2 times larger by diameter. And besides of that, what another frequency we are really interested in is to watch the universe in microwaves, because we have a cosmic microwave background. Cosmic microwave background is just the radic of the hot Big Bang itself. So that's super useful. And we also want to build the CMB telescopes. So, but to build the CMB telescopes, we want to watch in microwaves. However, microwaves are easily absorbed by water vapor. Water vapors can absorb microwave very easily. That's also the principle why you can heat up your food in microwave oven, right? Because the water basically absorbs microwaves. So you want to go to somewhere on Earth there is no water, right? Go where there is no water. We find a good place here in Xizang or Tibet, over there in Army site. Army site. Let's look at the global map. Here's the global map. These colors representing the amount of water vapors in the atmosphere. For the blue regions, they are suitable to build the CMB telescope. Yeah, because it's very dry. Very dry, very high, it's good size. So you look at. So for example, this position where it's Chile. The Chile, there's the Atacama Desert. The Atacama Desert itself is super dry and also very high and suitable. So people already put things there like that. And then in South Pole is also a good location over there. So also put like SPT and a bicep over there. And also have this location in Tibet or Xizang in China. That's also a very good locations over there. There's more than 5,000 meters. And also, these are the positions where you can do CMB observations on Earth. And you find, just from the map, you already have an impression that only very specific locations on Earth are suitable to do some kind of observation. Usually, a country itself cannot really own all the land out there. So the better way to do an international collaboration, to try to find the greatest spot on the Earth, and we collaborate together. Somebody choose the site, somebody to give some money, somebody else give the technology, and so on and so forth. To collaborate together and seek the mystery of the universe together. So, and a good example here is like SKA, there's this working array. You can see this photo, very beautiful photo. It's a photograph. It's not real. That's the plan. So on the left, these are the mid-frequency array. And on the right, these are the low frequency. And the mid-frequency array, they located the Central and South Africa. And the low frequency located at Australia. And in the northern part, southern part of the Earth, there's a pretty good site to do radio telescope. But you can find that there are somewhere missing here. So it's better we better have a bingo here. So the headquarters of SKA is in British. And have these two sites, and all the countries are participating countries. They contribute either. Like China contributed like 80% of the budget for SK. These are the frequency range. For the mid frequency, it's working from 250 megahertz to 15.3 gigahertz. And the low frequency working from 50 megahertz to 300. These dishes currently by far is contracted to a Chinese company called the CTC54. And that's also exactly the company who built the plate for Bingo. And this is also the company who built the plate for FAST. So we are really contracting the best companies in the world to build our telescopes. Okay, so by far you already heard about those telescopes we are currently doing or participating on what or just really finished by far on Earth. But look at the atmosphere window itself. You only have window here and a window here. What about the other range? Or here, or here, or here, or here. So for doing this kind of observations, the other frequency range of the radio of the electromagnetic wave, you need to go above Earth. You need to leave atmosphere. So we need to send rockets and send the satellites to do the observations. So this one is called dark matter particle explorer, DMP. To explore dark matter, basically we want to see gamma rays. Gamma rays are very energetic photons, most energetic ones. And so this DMP was artistically here. And this is the real image on Earth before it's launched. And in 2015, it's launched. Until now, it's still working perfectly. And it just gathered the data here to try to find the signature of dark matter with the gamma ray. And next one, this is the X-ray. X-ray is it's less energetic than gamma ray, but you also heard about the X-ray CTs. For example, when you go to a hospital, you have those CT scans, they are using X-ray. So that's the X-rays we also use to observe the universe in space. So this one, this is the real image before it's launched. And in 2017, it's launched to see the X-ray images. And then next one, let's go back to optical. Optical on Earth itself, even it's transparent. The atmosphere itself is transparent, but it's still nice that we have no atmosphere, dispersion, perturbation. So a good thing is still to send the telescope to space. So the very famous image I just showed you in the beginning of the talk, that's the Hubble telescope. Hubble Space Telescope is so famous, everybody like it. But how good can Hubble watch? This tiny window you can see, and you can see this little square. This little square is what Hubble can take a single time image just from this. And nowadays we are doing more cosmology. In doing cosmology means we want to watch a larger field of view. With a larger field of view, so here are some other telescopes currently, like for example, this blue region is W1 plan, and the Euclid in this square, Euclid was just launched, I think, 2 months ago, 1 month or 2 months ago, by the European agency. And here is another one that's by the blue lines that resemble the Chinese space station telescope, what we like to do. And it's going to be launched either next year or next year. And here is the artistic view of the solution. Artistic view, okay. So the light will come in this way and get into different cameras inside it. And another nice thing about it is if we find the telescope itself needs some repair, just like Hubble, when Hubble was first sent to space, we find that at first it doesn't really work well. And it needs some repair. So similarly, if you want to repair this or replace some new things inside the telescope, you can dock to the space station, and our astronauts, not really astronomers, can just go into the telescope and repair. And for the X-ray telescope, we also have a good band here. We have the X-ray called the Pro. It's going to be launched next month. Not really next month, this month. Some days later. I'm not exactly know. That's for X-ray. And also this one is for very low frequency, super low frequency, where on Earth we can also not observe. So the plan is to send these probes, you can see there are larger probes with many smaller ones, and send them to the orbit of the moon, to the lunar orbit. So when they rotate around the moon, with many different these little ones. Every one of those working as an antenna to form an interferometry array to watch the universe in very low frequency. So from 0.1 megahertz to 30 megahertz. And that's something we would like to observe, well, expect to observe. Yeah. And next one. So we're not only watching the universe in electromagnetic waves, but actually also in other ways around. Here is the new era called multi-messenger astronomy. I think that the world of multi-messenger astronomy becomes super popular. After 2016, we first discovered the gravitational wave. So we have cosmic rays, have neutrinos or gravitational waves. They serve as just different kind of flows. So here is a detector called LASSO, the Large High Altitude Air Shower Observatory. So this thing here over there in China, this location. This is a cosmic ray detector. So to detect very high energetic cosmic rays, when the very highly energetic cosmic rays come into Earth, they do not directly hit you. We are protected by our atmosphere pretty well. So it first hit some nucleus in the atmosphere, and then produce secondary particles, third particles will become a shower of particles. So just like a shower of particles, and all these particles will be received by the detector sphere. And here is a tank, many tanks of them. So this is a part. Compared to the size, this is a part, this is a tank. And inside of the tank, you can guess what kind of thing you put in the tank. Water. Very pure water. So when the energetic particles passing through the water phase, they will just produce light. And then we detect those very tiny light by pen inside these tanks. And so then you can reconstruct and say, yeah, we find a super energetic cosmic ray coming from somewhere. And next are two gravitational wave programs that currently we are planning. So one is called the Jiajun program. You can see this, there is a probe. This is the Jiajun test finder. So it's already launched in 2019 and successfully tested our technology of doing gravitational waves in the space. So finally, it's really true and really got funded. Where we can put 3 satellites around the Earth to form a network connected by lasers. 3 satellites connected by laser to form a network. Then this kind of triangle network can capture gravitational wave at this location. And next, another plan is called Jiajun. Jiajun also similarly forms 3 satellites as a network, also proposed to be launched in the 2030s. And so it will be planned to rotate around the sun rather than rotate around the Earth. So its orbit is over there. And the LISA is proposed by the European agency and the NASA. It's here. We were here. And this thing is also a real probe, real test finder will also launch in 2019. The next thing, neutrinos. Neutrinos can be captured by also very pure light, very pure water. When neutrinos passes through it, and by accident they collide with some kind of molecules or atoms over there. It will have some shiny light. So you need a very pure water there to capture the light, and you need the PMTs over there to capture the light. Then here's the program called the Trident. Trident. There's a neutrino telescope in the South China Sea, very deep in the sea. Just put many PMTs there to form a network like this to capture the neutrino signals from the universe. And this one was first the pilot project will be around 2026, and the full scale will be built in the 2030s. Well, again, if fully funded, funding is a big issue. And so here are all the kind of telescopes currently we are doing or we plan to do in the future. So we highly welcome for all kinds of collaborations. So if you are happy to know more about these programs, you can just contact me or you would like to participate in these projects, really participate in these, and you are a master student or undergraduate student, you might be happy to apply to our doctoral program for international students in our university. That's the University of Chinese Academy of Sciences. And so, thanks for your listening. Thanks.
Okay, thank you, Jiajun. Thank you for the nice talk. Questions, curiosities, perguntas, pessoal, pode fazer em português também. A gente pode tentar traduzir.
Yeah.
How about the trident? The trident telescope?
This one?
Yeah. How is the rate of detection of the neutrino? A day, a month, a year?
Not really sure. It's comparable to IceCube. IceCube is another neutrino telescope in South Pole. And I think it will detect neutrinos every day also. I'm not really sure.
Even a year?
In a year, we should see some events, but I don't really know how much time it is.
So about collaborations, in the next slide. So this is open for each time. How long people can stay in this collaboration? Living with students for years, or just short visits?
All kinds of collaborations. Short visits or longer ones, or you just apply really a PhD program, or adaptive. Yeah. We were basically open to all kinds of collaborations.
And professors or
Yeah, professors visits.
can be short, long, deep.
It depends on funding. Apparently, for these projects, we do not reject all the operations, but when you want to really visit us, you need some funding to support. But if you just want to collaborate remotely, it's much easier. That's how I do in the past 4 years for me. This was my first time to come to Brazil to really. In the past, I just participated in this program remotely. Yes. It's also totally fine.
Perguntas, pessoal. Aproveitem aí. I'm checking for questions if you have any questions in the chat, in the YouTube. Jiajun, can you tell us about, well, how is your day there in the Shanghai Observatory? How is the routine, for instance, for students who work there with you in the PhD program or master program?
Yeah, for
The subjects also, the subject of research, if you can talk a little bit about it too.
Oh yeah, for the subjects currently, I myself work. One is for bingo, that we are already and it somehow. And another one is for SKA. SKA, especially the SKA low, that's the low frequency array. Also to detect magnets. So this one, the purpose of my current research is trying to use this telescope to detect the 21 centimeter signal at the area of ionization, so higher resolution or farther away. And the third one I participate is about this one in the lunar orbit. We use the idea is to use the moon itself to block the signal coming from the Earth. All kinds of interference from the Earth itself are mostly man-made. So we want to avoid the Earth. So we send the probe to the moon lunar orbit so that when it goes to the far side of the moon serves as a really good blocker. So we use that environment to detect even further away from signals. But for now, because no one has even observed this kind of sky, so the very first thing is to observe what kind of sky looks like at those very low frequencies. So this is also another thing I'm working with. So if you are happy to, several different ways of collaboration. First way is to just send me an email and we can see, I can show you what kind of online meetings currently we have and we can do it together. And another way around is that if you really want to join our institute as a student, especially, you can apply for our program. It's possible. And if you are a PhD student going to graduate, they can also find our advertisement on AAS. You can apply for our postdoc programs. That's also possible. We have several postdoc positions open in our institute as well. So, these kind of ways. If you are already a faculty member, let's just talk about email.
Mais alguma pergunta, pessoal?
If this redesign to detect this not nanogravity, because it's not wave, but some intermediate gravity observations from the stars.
So you mean gravitational waves?
Yeah.
Oh no. This telescope has no ability of detection of gravity. It's only for radio waves.
I see certain, but people that are working on nanogravity, they using indirectly observation, not directly from gravity, but observation from both sides.
Both time phase.
So I mean, the people using can use it directly both sides.
Yeah,
Also, and indirectly, directly detecting some large wavelength for gravity.
Yes, I know. And for that we use this one. It's good enough. I think you are referring to the recent papers of shorter time array detection of gravitational waves at the level of around 3 signal or 4 signal. Nanograph takes like 13.5 years to reach that level, and fast will take 2 or 3 years. Because the sensitivity of fast itself is much. Yeah, just use our.
So this is the design.
It's existing. We can just contact and see how you can access to the data.
Actually, the mix of engineering world, semi.
So
Engineer,
engineers.
kind of engineer that Shanghai,
Okay.
engineers.
All the engineers. And so let me just take an example of this. You know that for doing a large interferometry array like these kind of antennas, every antenna basically need a receiver. You need a backend. So in Shanghai, we currently build the backend for MWA. So that's the pathfinder of MWA of this one. So we build the receivers. So currently the phase 3 of MWA as the pathfinder of SKA, half of the receivers was produced by our observatory. And we, besides the receivers, we also provide the hydrogen maser as provide, that's basically an atomic probe. We also build atomic probes ourselves. It's also by one of the best people. Apart from that, we also build like correlators to make the correlations of radio signals to form the interferometry. So these are the things basically that we are currently our engineers in Shanghai Laboratory is doing. They also do something else that I don't really know. Yeah. So yeah, there are quite many engineers who are sort of working on our observatory. Yeah.
This radio telescope Shanghai astronomers, they start computers. When
You mean
Shanghai,
Tianma, right? Let me see.
how was your knowledge there about the data storm detector?
Okay. So first, the two questions. The first thing about Tianma. I think Tianma started to build in 2009, around 2008 and 2009. It took 3 years. That's for Tianma. And about my own knowledge of
No, Shanghai asked the one, so how? What was the knowledge in China of the radio players back then?
back then. Oh yes, okay. Yeah, you may look at these new telescopes like sci-fi movies, but no, like 20 years ago we know nothing. Like 20 years ago we barely know. Our first radio telescope, very tiny, very tiny. That was in the 1980s. That's the first time that we tried to develop the very long baseline interferometry technology. For doing that, the very first dish we built is only 6 meters. Only 6 meter dish, and it serves like a toy beside this telescope. It's exactly really located there. We put it over there as a model. It's like a toy. And the story tells us that we just use this 6 meter telescope to test our own technology and get interferometry with German's Episberg 100 meter at this time. So you can see how big the difference is between our Chinese technology compared to the Western developed countries. But yeah, despite of that, we still believe that we ourselves can do, and so first we learn from the very advanced technologies from the world, and at the same time we try to develop ourselves. So after these like 20 years or so, we now have this sci-fi movie like telescopes currently. So that's exactly the thing I believe that Brazil can do. Brazil can really do. For example, Bingo is like the very first large radio telescopes currently we are building in Brazil compared to this one. We built it since the early 2000s. That's 20 years ago. For the same. And then this kind of thing is also super hard. We don't know how to do it, but we believe we can do it. So even though at first we learn quite a lot, or we just buy receivers, we buy plates, or buy many other things from different countries. But for now, many of these things we replaced by Chinese-made hardware ourselves, and we learned how to use it to do science basically in the whole process. So yeah, believe yourself.
Can you also speak a little bit, Jiajun, about this new connection now that we have with FAST and TL9 radio telescopes and Bingo?
Yes. So let's go to this location. Let's go to this. So the location of TL9 is here, and FAST is somewhere here. And in the opposite side of the world, opposite side of the Earth, that's Brazil. That's Brazil. And so if we can connect Bingo, or not really Bingo, but a successor, other kind of telescopes in Brazil, we connect those telescope signals to the ones in China like this. We can build this interferometry baseline, cover the diameter of the Earth. So that basically forms a Earth-sized telescope. So imagine how good it can be. And even further think about the programs that we can really collaborate. We also are thinking about sending some probes to space, and they serve as another radio telescope that we can also link together. So we can even go beyond the Earth and create such large telescopes So that's the foreseeable future, but we need our collaborations and help each other.
I guess another interesting point is that like Jianglai is a telescope devoted to FRBs.
At first, it's not.
Oh, at first.
At first, it's not.
Oh, I didn't know.
Yeah, in 2016, at first it's really designed to do 21 centimeter.
Oh,
We want to do that. But turns out that to do 21 centimeter intensity map itself is very hard. Okay, and very hard to do the data analysis. So they also installed the FRB backend to detect some FRBs. Similar things were happening for. So for us here, inside this tiny tree, to do 21 centimeter, they have put the 19 tiny forms inside to do the mappings and so on. But they also detected quite a lot of FRBs. Quite a lot of FRBs. Currently on Earth, we have detected around 3,000 events of FRBs. And actually, more than 2/3 of that is observed it. Right.
Is another potential can be this one, the study of FRBs from the three radio telescopes.
Yes, we can detect the FRBs together and to cover different regions of the sky.
What's the radius of isolation like this telescopes mean for to not have noise like broken area or something like that?
So you trying to say that how to avoid the interference from humans.
They need no distance, like to have a city or
Oh,
something like that.
the problem is not really about distance itself, but because if you sit in a valley, it's also fine because the mountains itself serve as a block, right? And sure, we need at least several tens of kilometers there. The best there's no one around, or at least no one holding cell phone. And that's necessary. But once you are really in a hill, blocked by mountains, don't really need to care who did anything on the other side of the mountain. It's already blocked by the mountain. Fine. For example, you can see this is Canada. In the back end, you can see the backside with the mountains. This mountain. So actually, it also located in a place where you have a flat land, but surrounded by some mountains. And we also asked the local government help us to protect the EM environment around. Beyond that, we cannot do too much. It's just inside of it. We need some prevention, protection.
I have a curiosity about the room first. When you put something wrong, you need to have good telemetry and a good model for calculating the order.
Yes.
Do you use GPL data or do you have your own data?
You talk about GPS.
GPL.
JPL. JPL. Wow. It's specifically talking about the radio antennas around the moon. The real information we really need to know and get to the work is the relative distance and relative position between the satellites. Where they really locate around the Earth itself doesn't really matter. You only need to know the relative distance, relative angle between those satellites themselves. So our current plan is to place lasers and LED lights on board those tiny probes and use those lights to capture each other. So just use those ways to see their relative angles, relative distance. Yeah.
Bom, pessoal, só fazendo um aviso, aproveitando o público aqui, né? Se vocês puderem, compareçam, por favor, na nossa cerimônia de abertura do evento da colaboração. Vai acontecer nessa quarta-feira, né? Às 8 horas da manhã, certo? Lá no auditório Rosa Tânia, que fica próximo da reitoria ali da UFCG, por trás do antigo auditório Zé Faria, né? Então, por favor, compareçam, certo? É muito importante que a gente tenha um bom público. A gente vai ter várias autoridades lá presentes, né? Inclusive o governador João Azevedo, secretários, membros da Agência Espacial Brasileira, do Ministério, talvez do Ministério de Ciência e Tecnologia. Então, compareçam, certo? Vai ser bem importante para a gente ter um bom público lá. Além dos nossos convidados, né? O Jiajun vai estar lá, a gente também vai estar recebendo o professor Wang, lá do chinês da colaboração, né? O professor Elcio Abdala, o pessoal da USP. Então, vai ser muito bom se vocês puderem estar lá com a gente. Certo? Professor Coffee Break, está lá às 9h30, mas não cheguem às 9h30. A gente vai tentar transmitir tudo online nos 2 primeiros dias. Então, a gente vai tentar transmitir toda a cerimônia de abertura online, também as atividades do primeiro dia de divulgação científica, inclusive. E no segundo dia, a gente vai ter uma série de palestras técnicas, né, que a gente também vai transmitir online. Certo? Então, eu vou colocar no site do evento o link do canal, mas vai ser no canal do nosso programa de pós-graduação, tá? E também vai estar lá na bio do Bingo, esse link para vocês acompanharem. Tá legal? Alguma dúvida mais sobre o evento, gente? Aproveitando aí, alguém quer perguntar alguma coisa? Os posters vão ser aqui na UAF. Aí a gente vai tentar viabilizar os painéis para o pessoal prender os posters, né? Mas uma emergência vai ser na parede mesmo. Mas a gente está tentando disponibilizar os painéis para colocar os posters aqui no hall. Vai ser no segundo dia, vai ser a última atividade do dia. Na quinta-feira.
De tarde aqui.
De tarde vai ser lá no Habimet. Aí depois da última reunião a gente vem para cá só para os posters. Tá?
Amanhã de tarde do Gabinete.
Quarta tarde vai ser no Rosa Tânia o dia inteiro, certo? Na quinta, segundo dia, vai ser no Labimet e os posters aqui. Ok? O professor Coffee Break vai ter lá no Rosa Tânia e no Labimet. Professor Coquetel aí é professor judeu, né? Cada um paga o seu. Ok, vamos agradecer novamente, gente. Obrigado, pessoal. Falei. Falaram que